So we're going to go back to when Bernoulli is useful. We started with that, and we're going to go back to that because it's really the critical issue with Bernoulli. Bernoulli is a really easy equation to use. It certainly gives important engineering results and important engineering insights when used appropriately. But because it's so easy to use and because it's so easy to remember, a lot of people misuse it. They just only remember the Bernoulli equation. They don't remember that it doesn't work a lot of the times. So I do want to reemphasize again just how many situations it doesn't work for and all the assumptions that it went into its creation. So incompressible flow. This is a really good assumption. As we've said many times, this often is valid. It's valid generally for liquids because they truly are incompressible. And it's valid for gases if their Mach number is less than zero point 0.3. That is, if they're traveling at less than 30% of the speed of sound. Generally, gas flows are also incompressible. They also cannot be treated as incompressible if gases have large temperature gradients because that causes them to significantly expand, change their densities. But we have isothermal as a condition down here anyway. And number two, this is by far the hardest one for Bernoulli to satisfy, is no friction or no viscous effects. As we said when we started, the only time you have no friction is if nothing is moving. So obviously these are moving fluids. There is going to be friction in all cases. In some cases, friction is very, very significant. In certain regions of the flow, friction is significant. If you have a significant frictional effect, then you can't use Bernoulli. So we got to be very, very careful with that. Steady state, important assumption. Obviously, many flows are not steady. Many flows are steady. That's fine, but it's important to be aware of it. Isothermal, that went into our derivation. The flow has to be isothermal, fundamentally almost the same temperature everywhere. Large temperature changes will cause changes in the density and make it not incompressible. It also invalidates the basis of the energy argument if large changes in energy are occurring. So if you have any kind of flow that has a chemical reaction like a flame or combustion, you can't use Bernoulli in that flow, at least not in the part that has the combustion. No work, which means no turbines or propellers in the flow. We said we can use it sometimes upstream or downstream of those propellers, but in the region that has the propellers, you're going to have work. Also, of course, in the region that has propellers, you're going to have a lot of friction. So that's going to invalidate the analysis for two reasons. Technically, Bernoulli is valid along a streamline. That is, the constant, Bernoulli constant is constant along a particular streamline. We haven't really discussed streamlines yet. We will discuss streamlines later. Leave it at this point to say that that's not really a problem usually unless the flow is rotating and spinning, and that doesn't happen if there's no friction. So generally speaking, although this is an important mathematical condition for Bernoulli constant, from a practical point of view, it rarely comes up if you have these other conditions satisfied. So here are some just pictures of when you can use Bernoulli and when you cannot. Bernoulli is often used in what are called external flows, so flows that are not contained inside a pipe or a channel or anything. They're just flowing around an object in an external environment. Bernoulli is good when you're far from the object, away from viscosity effects. Near the object, this is supposed to be a picture of a plane. You're going to get the no-slip condition on the surface of the plane. That's going to cause the velocity to go to zero. There are going to be viscosity effects all around that. So Bernoulli's not good in there. It's also important to point out that the stagnation pressure, it does not occur when it's caused by frictional effects. We know that all surfaces cause velocities to go to zero, but the pressure will not be stagnation pressure in there because Bernoulli does not apply there. That zero velocity is caused by a viscous problem, not by the decrease in velocity per se. So stagnation only occurs in cases where the velocity goes to zero without viscous effects. Similarly, in the wake of the plane, there's going to be all this swirling, turbulent flow, and that's going to have lots of viscosity. So in the wake of the flow, it's not going to be any good. Bernoulli will not work. So you have to be, kind of far from the plane for Bernoulli to be valid here. If you're looking at turbines and propellers, people do use Bernoulli in the upstream section of the flow. And then in the downstream section of the flow, you can sometimes use it, though you have to worry about wakes in the case of propellers and turbines. But if you're out of the wake zone, It may be that Bernoulli can be used both up and downstream, but if you do that, it's going to have different Bernoulli constants. The upstream and downstream portions are going to be different because energy is going to either have been added to or removed from the system by that propeller. If it's a propeller that's turning, it's going to add energy. If it's a turbine extracting energy, it's going to reduce the energy of the flow, but either way, the Bernoulli constant will have changed from the upstream to the downstream situation. Finally, Bernoulli is used a lot in pipes, tunnels, and channels. This is in some ways the riskiest. We know the Bernoulli is only valid if you're away from the wall. At the wall, you're going to have definitely viscous effects. Those wall effects are going to go increasingly into the pipe as the flow continues down a long pipe. At some point, there will definitely be a flow that is completely dominated by viscosity and does not have any regions of what's called inviscid or non-viscous flow. So whenever you're in a channel or a tube or a pipe, there is a real concern about whether Bernoulli is appropriate. But nonetheless, in some types of flows, Bernoulli is used successfully in pipes and channels.